which I totally depend upon you guys. Okay. Anyways. So saturation flow rate. How do we calculate saturation flow rate? Tell me. Just a hint, it is calculated using another term which has the word saturation in it. And we have used it in all the examples we have done in this chapter so far, in this topic so far, we have used that term. What is that? If I ask you to calculate saturation flow rate for me, what do you ask from me? Anyone?
Maybe it's the capacity flow rate.
No. Saturation capacity? No. Flow rate. How do we calculate flow rate? Capacity comes from saturation flow rate, not the other way around. How do I get saturation flow rate? Anyone?
Determines number of cars and peak factor and peak times.
No. Ashim, wrong again. Like I said, it comes from a term which has the word saturation in it, and we have used that term throughout this topic. What is that? Saturation dash. What is this dash? Who will tell me? Yeah. Finally. Saturation headway. Okay. Headway is the inverse of flow rate. So if you take the inverse of saturation headway, you get saturation flow rate. Okay. The saturation flow rate comes from saturation headway. Okay. So the saturation flow rate is the rate at which the Q departs from the intersection, and that is represented with small s. And how to get it? Take the inverse of saturation headway. So this is the line showing the arrival of vehicles, and this is the line showing the departure of the vehicles. So if you take the difference between these two lines, it will give you the how many vehicles are in the queue. How many vehicles are in the queue? Because what? This is the number of vehicles. This line is showing the number of vehicles which arrived, and this line is showing the number of vehicles which departed. So whoever arrived and didn't depart is in the queue, right? Simple. Whoever came and did not go is in the queue. So if you take the difference between the arrival flow rate line and departure flow rate line, you will get the number of vehicles in the queue. Okay. So how many vehicles are in the queue at time t? This is QT. Okay, QT. Now, if you want to calculate time in queue delay for any vehicle. So let's say a vehicle came at this time, and how much time it has spent in the queue. Again, the difference between the arrival and departure line, but horizontal difference now. Time, okay, I'm talking about time in queue. So I want the difference on the time axis. Okay, so if you take the difference between the arrival and the departure line horizontally, you will get the time in queue delay, the time the vehicle has spent in the queue. So it arrived at this time and it departed the intersection at this time. So between these 2 points, this is the time in queue delay for vehicle I. Okay, so in this figure or using this graph, you can find out the time in queue delay as well. Okay, so now in the previous graph is for uniform flow condition, and again other names given to uniform flow condition previously are undersaturated, below capacity, okay, or sustainable flow. These are the terms which we use to indicate the uniform flow condition. Okay, and how do I know this is uniform flow? Because you see we started when there was no queue. Okay, this is one indication. Another indication that during green time there was a point where there was no queue, and you can see before the green interval ends, the queue is totally cleared. Okay. If you don't have uniform flow conditions, if you have the opposite of that, which is called as queue buildup condition or oversaturated conditions, then the queue will not end till the end of green. The queue will not be clear till the end of green. Okay, so uniform flow means the queue will completely clear during the green interval. Okay, and which is happening here. Okay, so from this point onwards, it will follow the same pattern at the start as the start. Okay, from this point onwards, it will follow the same pattern like we have done so far. Okay, so this is for uniform flow conditions. For uniform flow conditions, Webster, he was a scientist, and he said if you have uniform flow conditions, the flow is under capacity, then the delay is also uniform. That is, a delay for each week is also uniform. So in 1958, he gave an equation for calculating aggregate delay, total delay for all vehicles. And this is the equation, the first equation on the slide, UDA equals half R into V, where R is the time of the red interval and V is the number of vehicles which experience the queue, which join the queue, total number of vehicles which join the queue, that is capital V. Okay, so half R into V is aggregate delay, total delay for all vehicles, and you can see it's a very simple equation and it is still being used since 1958. Okay, so simplicity is sustainable. Simplicity is sustainable. Okay, the more we make things complicated, it doesn't last for long. Okay, like our mobile phones and our laptops. Since last couple of weeks, I am be thinking that my laptop is outdated now. Okay, I have to change it. Even just before the previous lecture, I had to restart it just to make sure everything was working fine. Okay, so with the advancement in technology, things are becoming more complicated, and we need to the need to update is also becoming, very rigorous. Okay, but coming back to the Webster's simple world of this equation, aggregate delay is equal to half R into V. Now let us expand this equation. We don't like simplicity. Let us expand this equation. So we will start the expansion with R. So R is the red interval. Okay. Now earlier I have said that you can divide the signal cycle into two parts, two distinct parts. One is called as effective green and the other one is called as effective red. So effective green is the time of the cycle during which the vehicles are moving at saturation flow rate, or the interval between the vehicles is equal to saturation headway. The time of the cycle during which this is happening is effective green, and whatever is not effective green is effective red, R. Okay, so if you want to calculate R, the time interval for R, and you know the portion of cycle length which is effective green, then whatever is remaining, that is effective red. Whatever portion of the cycle length which is not effective green is effective red. So you can see the equation for effective red are here, G by C, which is the portion of cycle length which is effective green, 1 minus G by C, meaning the remaining cycle length, and you multiply with the cycle length itself to get the time for that interval. So let's say G by C is 60%. 60% of the cycle length is effective green. So 1 minus G by C will be 40%. So 40% of the cycle length is red, effective red. Okay. So R can be calculated using this equation. For calculation of V, now pay attention here because we need to do a lot of things. So V is number of vehicles in the queue. Number of vehicles in the queue. Now, you can see the same graph is pasted here with another term which is TC. Okay, so this is the red interval, and red interval equals to this. We already said it. And then we have TC term. TC is the time to clear the queue when the signal becomes green. After the signal becomes green, how much time you need to clear the queue? TC. Okay, so you can see TC is from the start of green till the point where arrival equals to departure. That means the queue is completely cleared. During this time, the vehicles are moving at a rate of S, saturation flow rate. Okay, so S is saturation flow rate, vehicles per unit time, and if you multiply with the time, you will get number of vehicles, right? So how many vehicles were in the queue? S into TC. Okay, they were moving at a rate of S during time TC, so they cleared the queue. So how many vehicles were in the queue? Rate into the time they took to clear the queue. Okay, so S into TC will give you V, number of vehicles in the queue. Okay, this is one way of calculating number of vehicles in the queue, which is to use saturation flow rate, the departure flow rate. Another way to calculate the number of vehicles in the queue is to use the arrival flow rate, V, small v. Okay, now when did the queue start? When did the queue begin? It began when the signal became red. So whoever came during this, from this point till the end of TC, from the start of red till the end of TC, was in the queue, right? Because whoever came after TC, he did not find any queue and he just continued moving. Okay, so from the start of the queue, from the start of the red, the queue started to happen. So whoever came after this point till this point had to join the queue because he found some vehicles in the front of him or the signal was red for him. So if you take the arrival flow rate and multiply by this complete time, you will still get the same number of vehicles, which is the number of vehicles in the queue. You will still get the number of vehicles in the queue. So number of vehicles in the queue can be calculated using the saturation of the departure flow rate, which is S into TC, or you can use it, or you can calculate using the arrival flow rate, which is V into R plus TC. Vehicles arriving during which time? R and TC. All these vehicles were in the queue. Okay, and obviously we are talking about the same queue, so S into TC must be equal to V into R plus TC, and this is what we are saying here. This is using the departure or the saturation flow rate, and this is by using the arrival flow rate. But we are talking about the same queue, so the quantities are equal. Okay, and from this equation, I can calculate the value of TC. I can find out the equation to calculate TC. Okay, now the TC will be put back in the equation of capital V. Now capital V is number of vehicles which joined the queue. We said it can be equal to V into R plus TC using the arrival flow rate. And in this equation, I already have the equation for TC from here. So I will take this equation of TC and put it instead of TC. Okay, so this is the equation. And if you open the bracket, take V inside and then multiply all the terms and then take R as common. This is the equation for V then, number of vehicles in the queue. Okay, this is the number of vehicles in the queue. Okay, and then in this equation, we have the term R, and we know R equals to C into 1 minus G by C. Okay, the remaining proportion of the cycle length, which is not effective green. So R can be replaced with this. Okay, so this is the final equation for V, number of vehicles in the queue. Going back to the Webster's equation for aggregate delay, half R into V. So I have an equation for R, which is this one, only this one. And I have an equation for V, which is this complete term. So if you multiply R with this complete term, the equation of R with this complete term, you will get this. So this is the final equation for uniform aggregate delay. Okay, so you can see he's using the subscript A here. A means aggregate, total. Okay, and you will get the answer in vehicle seconds or vehicle hours. Now, if this equation is divided by number of vehicles arriving, then you will get the average delay. This is the total delay divided by the number of vehicles, you will get average delay. So this whole equation divided by the number of vehicles arrived, you will get uniform average delay. And this is the equation for uniform average delay. Okay. Now, in this whole derivation, whatever explanation I have given you, do you have any questions regarding that? Any questions about what I have explained? I have done a lot of explanation. If you have any questions, go ahead, ask me. Clear? Is it clear? Everything is clear? You know the derivation will not come in the exam, but at least you know the term and how did we derive the equation. Is it clear? Okay. Now we have a term which we called as V by C ratio, volume upon capacity ratio. We have used it in the equation of cycle design, signal cycle design, and we have used it earlier when we were calculating the delay for roundabouts. Okay, so the same term, if I can include V by C ratio term in the equation of delay, then I will have two terms which are common between the equation of signal design, which we use to calculate C, and the delay. Okay, so I will have two terms which are common in the equation of cycle length and the equation of delay. The first term is cycle length itself, and the second term will be V by C ratio. Okay, and why do we incorporate V by C ratio? Because we don't want the capacity of the signal to be equal to the flow rate in the peak hour. We want the capacity to be higher, even than the flow rate in the peak hour. So we incorporate V by C ratio. In the equation of cycle length, we just added the V by C ratio. We just divided the volume with the V by C ratio as it is. But in the delay equation, we have to do some working here. Okay, I cannot directly put the V by C ratio here because it is not. We are not talking about the capacity or something. Okay, the equation does not have the term capacity here. So what we will do, the first example which we did in this topic, we use this relationship. What is this relationship? Capacity equals saturation flow rate into G by C ratio. A small c is capacity, capital C is cycle length. Okay, must keep the difference in mind. A small c capacity, capital C cycle length. Okay, so how did we get this relationship? We said saturation flow rate is the ideal value, hypothetical value, imaginary value, which you can get if the complete cycle length was equal to effective green, meaning if the G by C ratio was 1, then capacity will be equal to saturation flow rate. Okay, since since the complete cycle length is not equal to effective green, G by C ratio is never equal to 1, then you will only achieve a portion of saturation flow rate as cycle length, as capacity, and that portion is equal to the portion of cycle length which is effective green. Let me say it again. You can only achieve a portion of saturation flow rate as capacity, and that portion is equal to the portion of cycle length which is effective green. Okay, so again, if G by C ratio was 1, then C would have been equal to S. If G by C ratio is 60%, then capacity will be equal to 60% of saturation flow rate, and so on and so forth. Okay, so in the previous term in this equation, I have the term S here. So using this relationship, I can derive the equation for S. So S equals to capacity upon G by C ratio. So I will remove the term S and replace it with this thing, this ratio, capacity upon G by C ratio. So in the denominator, instead of S, you will have this now. It was V upon S will become this now. Okay, and V by C ratio, as we have done in the equation of roundabout delay calculation, V by C ratio can be represented as X. So what is X? V by C ratio. Okay, so this is the final equation with the V by C ratio for uniform average delay or average uniform delay, seconds per week. Now let us look at a small example. We have an approach which has a flow rate of 1000 vehicles per hour, saturation flow rate of 2800 vehicles per hour, cycle length is given, G by C ratio is given. We need the delay per vehicle. The equation of delay per vehicle is this one. In this equation, I have the cycle length, I have the G by C ratio, I need the value of X. Now X is volume upon capacity, volume upon capacity, or flow rate upon capacity. Flow rate, arrival flow rate is given 1000. I need the value of capacity. I need the value of capacity. From the data given in this question, how can I calculate capacity? And a hint, I've just explained it right now. Just before starting this example, I've explained it. So using the data given in this question, how can I calculate capacity? I've already explained it. Tell me, how can I calculate capacity using the data which is given in this question? Anyone? Take a guess, no problem. You are given with arrival or approach flow rate, saturation flow rate, cycle length, G/C ratio. Using G/C ratio, yes, good. So use a G/C ratio like I've explained earlier. Okay, so capacity equals S into G/C ratio. S is 2800. G/C ratio is 0.55. How much is this? How much is this? $15.40, okay. Meters per hour per lane. Okay, then how much is X V/C ratio? How much is this? Sorry?
0.65.
Okay. Okay. How much is this uniform delay now? Sorry?
9.5.
9.5. Is it 9.5? Okay. 9.5 seconds per vehicle. Okay, where's average delay? So seconds per vehicle. Okay, so I will stop here. This is the end of this topic, and we don't have the time for any new topic. So, any questions? Any queries? Any problems? Cycle length is 90 seconds. Sorry, what did I write? Okay, this should be 90 seconds. Sorry. Give me the value with 90 seconds. 14.2. Okay, thank you. Any other problem? Any other questions?
Victor?
Yeah.
I have a question regarding the project.
Go ahead.
So the due of the project will be in 26 or 23?
26, right?
It's written in the syllabus 26.
26. 26.
Okay, what about the presentation?
Next week.
Okay, the presentation should be recorded or what?
No, live in the class.
So you will perform a live for just for the presentation?
Yeah.
Okay, thank you.
Doctor, can you rephrase what you said at the start about the free flow speed methods? Because it wasn't recorded and I didn't hear you.
Free flow speed can be calculated in two manners. First, for the intersection, first of all, take the spot speed data, before the intersection on the same segment of the road which is coming towards the intersection, but at a point which is not affected by the queue of the intersection. So this is one way of doing it. So the speed which you get at that point can be considered same as the speed you will get at the intersection. Another method is when you have the green phase and there are no vehicles in the queue. So if you measure the speed of the vehicle which comes during that condition, it can be considered as free flow speed.
Okay,
but obviously, again, you don't rely on one value. You will take multiple values, but all these vehicles must be passing through the intersection in the same condition, that when they came, there was no queue and the signal was already green for them.
Okay. And about the presentation, Doctor, because the people with me are from section 1, so we're not going to have the same lecture timing. So how can it be done?
You can, if some of you can manage to come in one section, fine. Otherwise, you do it in your own section, no problem.
Is it okay if I do it on everyone's behalf?
No.
Because what if, let's say, they have other lectures or there's a time conflict or something and they can't?
No, this is what I'm saying. How many are you in the group?
We're 3 people.
3. And what's the distribution? How many are in from this section?
I'm the only one from this section.
Okay, so you present your part in this section and they will present their part in the other section. No problem.
Okay, Doctor. Thank you.
Okay. Anyone else has any questions? Okay, then all the best. I'll see you guys on Thursday, inshallah. Have a nice day today and tomorrow. And yeah, thank you. Assalamu alaikum.